Whether in space or on a different planet much farther from Earth, the utilization of nuclear energy and a steady electricity supply can accelerate, improve, and reduce the cost of interplanetary travel. NASA-backed SpaceX nuclear rocket technology could set the stage for future space travel. What exactly is this space technology, and how does it function? Join us as we investigate how SpaceX's insane nuclear Starship has taken the entire space industry by surprise. Well, first off, the Starship could dramatically reduce travel times to remote locations, improve launch flexibility, and keep astronauts safe during space flights. It may also decrease the risk of hostile threats on satellites. A rare merging of technological financing and political will is on the verge of launching spacecraft. Nuclear reactors are becoming more common as NASA continues to pursue its Apollo-like Artemis mission to build a crew lunar colony. With a vengeful human in mind for landing on Mars, the White House has set a 10-year target for NASA to produce a 10-kilowatt nuclear power framework for the moon's surface. The project is currently the top priority of the agency's Space Technology Mission Directorate. Plus, the Congress appropriated $110 million for NASA to advance the development of a new nuclear rocket. NASA will move forward with the development of a new nuclear rocket capable of transporting people and cargo to other planets. The funds were not even demanded by NASA. The obvious reason for this enhanced sense of urgency is the space agency's stated goal of establishing a moon base by the end of the decade, which is difficult, if not impossible, to achieve without nuclear power. To say nothing of putting boots on Mars, developing a nuclear reactor for spaceflight requires no major technological advances. In reality, the US has only completed this once before, in 1965, when the Air Force evolved and initiated a functional prototype. Consequently, the challenge is navigating the dense web of laws that regulate all of its nuclear power and ensuring that every methodology adopted to use nuclear power outside of Earth doesn't limit NASA to the lunar surface or any other separated deep space destination. Ideally, the authority of the particle can be utilized for robotic solar system exploration in addition to primitive Moon and Mars missions. To understand thrust, which underpins rocket propulsion, assume releasing the nozzle of an air-filled balloon. When the air manages to escape the hole, the balloon is pushed in a reverse way. The force trying to push the balloon is known as thrust. A large percentage of rocket engines initiate a mixture of fuel, such as liquid hydrogen, and oxidizer, such as liquid oxygen, to generate lift by pressuring gaps out of the engine's nozzle, causing the launch vehicle to be propelled in the opposite direction. However, there are other options besides chemical rocket engines. Nuclear thermal propulsion systems are twice as efficient and potent as chemical rockets. Since the 1950s, NASA has been researching systems that use nuclear effectiveness to create the required energy to convert liquid propellant into gas and produce thrust. Although chemical rockets will be employed to release spacecraft from Earth's surface in the coming years, these technologies have huge benefits for space travel. NTP systems can double their thrust while using the same quantity of propellant, making them more powerful and twice as effective as chemical rocket engines. Experts estimate that lowering the time it takes for a rocket to attain Mars by up to 25% or roughly 2 months will reduce dangers to astronauts such as cosmic radiation, weightlessness, and exhaustion. The use of NTP engines also would improve the flexibility of missions to Mars, which currently has only one launch window for a crewed chemical rocket. When the Earth's and Mars orbits are fully matched, which only happens once every 26 months because of the weight of the fuel and the NTP system's efficiency, a mission to Mars is launched. It would therefore require far less fuel than a chemical rocket. The powerful machine will indeed enable trips to occur even when Earth and Mars were not in their ideal locations to reach Mars, and a quantity of uranium barely larger than a marble. That's great if you absolutely cannot wait 2 years for resupply or rescue. Nuclear propulsion will indeed expand the range of crewed travel options while reducing the number of flights required to transport the fuel for such a journey into Earth's orbit. The International Space Station, which tips the scales at about 420 metric tons and was meticulously built throughout more than 30 launches, has significant fuel requirements. Over a decade, it would be incredibly expensive to loft more than twice as much tonnage from Earth for a chemical launch vehicle required for a round trip to Mars. Keep in mind that the Orbit Launch System SLS, NASA's most powerful rocket ever formed, has yet to launch and is only intended to lift 95 metric tons into space for $2 billion per launch. If and when the SLS is supplanted by more competent and reasonably priced rockets like SpaceX's in development and all-recyclable Starship, their single-launch tonnage restriction will start rising to more than 100 metric tons, and the cost per launch should fall. The 120-meter-tall Starship fundamentally changed how space scientists conduct their work, empowering human exploration, establishing bases on Mars, creating a multi-planetary species, and saving civilization from extinction. If SpaceX's predictions of cargo initiation costs as reduced as $10 per kilogram are correct, larger and heavier detectors could be transported more frequently and at a lower cost. On Mars, rovers could be launched in groups rather than as individual fleets of satellites on Earth. Orbits could become more common, and space telescopes may help to advance the fields of astronomy and planetary science. Earth observation could all boldly advance the Falcon 9 SpaceX, which is 70 meters taller. Workhorse rockets have already transformed the aerospace industry by directing the first phase to a landing when it re-enters the atmosphere using vintage rockets and steerable fins. With that rocket, SpaceX invented reusability. The company plans to launch more than 50 Falcon 9 and Falcon Heavy rockets this year. This works out to, well, almost one launch per week on average, which allows SpaceX to charge $67 million for a Falcon 9 launch, which is markedly less than its competitors' other reliable reuse and fast launch frequency. Elon Musk, on the other hand, was not satisfied. At an international astronautical congress in Mexico, Elon Musk drew design concepts for a rocket to colonize Mars. The rocket has been later known as the Big Falcon rocket, and in more family-friendly terms, the concept was developed into Starship, but the focus on cost and reusability persisted, making launches as boring and pointless and prevalent as FedEx cargo flights. The rocket's body is made from stainless steel, which is both more costly and simpler to manufacture than aluminum. Most rockets use alloys, but the 33 Raptor engines squished into the back of the Super Heavy use heavier methane instead of the traditional kerosene-based rocket fuels. Not only is it less expensive, but it can also be generated on Mars by combining water and carbon dioxide after a 6-minute journey. Each machine should be capable of launching 3 times per day, and a tanker variant of the vehicle could refuel a loaded Starship. Once in orbit, it could be capable of transporting 100 tons of payload to the Moon or Mars, but on an interplanetary scale, nuclear heat propellant would primarily take the shape of a ferry or transfer stage, a relatively small nuclear-powered rocket that would disembark in orbit with the other transit components before launching its payload. Meanwhile, the combustion chamber, where a rocket fuels and oxidizes a mix before igniting, is overtaken by a nuclear reactor that warms a cryogenic propellant and blasts it through the spout to generate thrust. This arrangement works in a similar way to a chemical propulsion system, and from the outside, the procedure looks like a rocket engine on fire. The main issue with nuclear thermal propulsion is that it employs a high-performance reactor that operates at high temperatures, which is frightening for astronauts and material engineers. The reactor would require massive amounts of cryogenic propellant, which would most likely come from on-orbit storage tanks, which also present their own set of engineering challenges. However, there is a benefit to the method's obsessive focus. The propulsion system only must be running for a few hours total until you complete all of your work quickly, after which the spaceship has all the speed it requires to get to Mars or back to Earth. That's a wrap for this video. Share your thoughts on nuclear-powered spacecraft in the comments section below. Don't forget to give a thumbs up and subscribe to our channel for more videos. Bye!